While you're watching this webinar, we'd love it if you'd follow us on social media at Twitter, Instagram, and Facebook at Greendale FTC. We'd love to connect with you.
Our first speaker is Richard Shook. He is the Senior Mechanical Engineer at AMPCO Pumps. He is going to give us a presentation about the basic principles for the development of custom parts for industrial equipment and in CAD programming. And Mr. Shook, go ahead and share your screen for your presentation. Thank you.
Okay, sounds good. Hello, yes, as it was mentioned, my name is Richard Shook from AMPCO Pumps Company. We are we are actually a manufacturing facility that produces sanitary equipment for the food and beverage industry. We also do industrial products for applications such as paper mills, paint, chemical injection, but we'll also get into pharmaceuticals as well. And from what we typically do, what I'm involved in, I'm on the design side of things. So on a day-to-day, a customer will actually come to our sales team and provide them with potentially some specs or just general questions about an application that they have. And then the sales team will actually take all of those. They'll compile a list of everything that we do have available and whatever we don't. And whatever we don't have, then they come to me and say, hey, this customer needs something new and custom, so you're the guy to develop it. So that's what we're going to talk about today, is the development process that I use in order to do those parts. But the first thing I wanted to kind of get into was regarding the, let's see, it's kind of going over what we do as a company. So a lot of the pumps that we design for, as I mentioned, for the food and beverage industry, a lot of times we'll have a number of customers with very specific needs that extend outside the capabilities of our standard product line, like I mentioned. And because we're a small manufacturer, we, unlike larger companies like SPX and Alfa Laval, we are able to kind of change and adapt a little bit quicker on the fly for a lot of our customers and still kind of meet within the same parameters as those larger companies. And so because of that, and because we're small and can do all those things, it actually gives us the freedom to pick and actually review all different types of manufacturing methods. And so that's actually where we're going to start because I think it's important to have at least an awareness of what the different processes are. And once we know what's out there, then we can take steps to the development process. So starting off, there really are like 4 major types of manufacturing methods. There's the traditional method that most people are familiar with, the CNC machining. There's lathes, mills, and so forth. There's usually some sort of honing or something involved in that as well. And then there's the additive process that a lot of people are familiar with. And that will kind of cover a little bit more of the 3D printing and so forth. There's consolidation processes such as welding and bonding. There's some other unique stuff that's in there as well that we don't really get into, such as sheet metal. We do some parts here and there, but for the most part, we stick to just kind of basic welding with tubing. But we still get a chance to actually explore some sheet metal through our design process. And then there's deformation. There's like molding, and injection molding is actually a really common thing. Or if you guys are aware of hydroforing, that's kind of really popular. I believe the mid-2000s F-150. The frame was designed using aluminum water forming for the whole frame, or for the chassis. So that was something that's new that we've actually also considered for some of our products. So I wanted to highlight here on the right-hand side here, we have a pump that we've developed kind of custom for the tomato industry. It's something that kind of incorporates a lot of different manufacturing processes. And I highlighted here that there are there's some castings involved. There are some forgings involved with the fittings that we use. And then also the tubing that's involved there, that's actually an extrusion process. So again, it's really just kind of having an awareness of what those look like and what they are. We don't really need to kind of go into actually how all the specifics for each one of them, but it is important to just know that they're available. As I mentioned, castings, 3D printing. This is an impeller that pulls in air and water, and that helps our pumps to not get waterlocked. Something like that is actually, because of the complex geometry, we do have to do a 3D printing process for that. So we're actually currently getting that developed right now. We actually should see prototypes within the next few weeks. Another option is sintering. Sintering is kind of a unique bonding consolidation process, but it's also kind of casting in a way too. It's basically taking a mold, pouring in powdered metal, and then compressing it to high pressures and then temperatures as well. Well, sometimes high pressures, but essentially it basically, with the high temperature, it fuses everything inside together. There's usually some bonding agents involved in that as well. But usually that's meant for like seal faces. You can typically find like jewelry as well in those same applications. And then there's welding and brazing, bonding, rolling, and punching. And this image here on the right kind of just shows where a lot of that takes place with the products that we develop. So really, with all of those different processes, you're probably wondering, how do we decide which one when you are at the beginning of a project? It's really daunting, but as I mentioned, as long as you can keep an awareness of what is available out there and have that at the forefront of your mind of what you think you could be going with your part, then that's kind of where we'll kind of start with step one, is defining the functionality. So as long as you know whether or not it needs to move, how does, statics and dynamics, I guess, essentially, where are your reaction forces? How does it interact with other parts? Is this going to be something that controls an arm of some sort? Taking this kind of a little bit back to pumps, are you going to deal with chemicals such as caustics, so like hydrochloric acid or sulfuric acid? If that's the case, then you're probably going to need something that's made out of potentially stainless steel, which kind of limits also the manufacturing process that you're going to be using. Steel is not really good with hydroforming, but you can cast it, you can mold it, you can do a lot of other things with it. So that's one method there, or one step there. And then also you want to consider the regulations and codes that are involved as well. That's really just to kind of get involved a little bit deeper in the history of the functionality of your part, to just know, if you're building something for human interactions, then there are certain regulations that you have to meet for that. If you have to do industrial equipment, or you're building something for a processing plant, almost all of your regulations are going to be coming from OSHA, and just because the safety is hands down one of the most important things that you ever have to encounter in your professional life. Other organizations and regulations that you'll probably deal with are the FDA. They control not just the foodstuffs, but also your cosmetics as well. But then also it goes into pharmaceuticals with your well, with what kind of we're dealing with right now with the pandemic. So yeah, we get involved with that a lot too. And then also 3A is another regulatory body that we deal with. They actually set the design standards for what we do in the food and beverage industry in order to meet the FDA requirements. So when we're doing a lot of our initial design, we actually have to document a lot of what is prescribed in these standards. And usually once you have an idea, you have of what you want to make, you have a general understanding of what the definition is of your functionality, and then the standards kind of just lay everything out for you. And then you just kind of follow in line from there. The next step really is then establishing what sort of forces are going to be acting on the part that you have. You can look at things like a free body diagram is a great way to kind of map out your part. Or if you're designing a robot, you can start off with the whole system and then kind of break down into each component, or you can work your way out from component to the full assembly method. Either way, it's really important to start off with the free body diagram. Because that's just going to be a visual way of taking all of that information and putting it into a very nice and easy way of understanding, where things are going to interact and where might you be able to save some cost. One thing that's popular with casting is finding, just different areas where you can actually remove material. Whereas with additive manufacturing like 3D printing, that's not something that you really have to worry about too much. Until you start to get into printing metal, then it becomes a little bit more cumbersome with just the structural nature of the part. After drawing the free body diagram, and so I guess, sorry, I should go back. So when you're drawing your free body diagram, the first thing you really want to do is establish your frame of reference. Are you in a 2D space, a 3D space? Do you have to also consider things like vacuum in your environment? Are you underwater? Those kinds of things. So you really want to establish like all of your givens, and then you lay out all of your forces, and then you determine your reactions, find your unknowns, and that's going to give you the strength of your part. And that kind of ties into selecting the material, because with the 3D printing process and with all the other different manufacturing processes, you do have some limitations as far as what materials are available and the strengths. And so when we start to look at the material selection portion of it all, what we typically use in engineering is what's called the Ashby charts. This is just one example here. This is showing the strength of materials relative to their weight. So this will, once we kind of know what our forces are, then we can actually go to this chart and figure out, which family do we generally want to be within. So we can draw certain lines, such as maybe weight is a huge issue, so you don't want to weigh down other components. Maybe that's a factor that you have to deal with, such as if you're dealing with like aluminum or polymers. Those interactions will affect the other materials that you use for those parts. So to help us also achieve those selections, we have tools such as FEA, which is a finite element analysis. At my company, we use SolidWorks simulation. So that allows us to do a lot of the structural analysis up front to determine, based on the shape that we've kind of initially laid out, where we think we could be at in terms of material. And then we can kind of fine tune from there. To give you an example, down on the bottom left here, we have a shaft with an impeller attached to it. This is a project that we had where we were developing a high pressure version of a pump that we already produce. We found that the shape of the rotor was best to be this lobe, tri-lobe type shape, because it distributes the force from the suction side to discharge side a lot more evenly than if we were to do a bi-wing design or a more complex lobe design. So keeping it simple to just try lobes actually helped us out with reducing the amount of stress that you see on the shaft where we have a point of potential bending failure. Because of the shape, we were able to find our yield strength, or sorry, we find our yield point of the shaft, and then based on the bearing, based on our fixtures from the bearings, we were then able to find a material that best suited this application. So what we chose for this one was a 17.4 stainless steel with an H11 heat treatment. That got us up to 126,000 PSI in terms of the yield strength. And as you can see, the high point of the stress that we're seeing here is 24,000. So sure, yeah, it might have been a little bit over-engineered, but we are accounting for fatigue life as well. You do also have to incorporate that when you're looking at what kind of materials you're looking at. So when you go through a lot of these tools and selections, you can probably turn into like an iterative process almost, where you might get through all the way to step 5 and realize that, okay, well, maybe I don't need to use steel anymore. Maybe I can solve all of this with just plastic, or maybe get away with titanium and do something fun. And so that's kind of where we go into step 4, which is essentially just knowing what those manufacturing processes are. And now we've determined, or now we have to select one. So in order to select one, you really want to know what the capabilities are. And that includes, are you going to have a 3-axis design? Are you going to have a 4 type? Perfect. Okay. So then once you've determined the capabilities of each of the different manufacturing processes, you also want to look at the limitations. So things like 3D printing, the limitations there are the material selections that you have available. 3D printing does really good with polymers and plastics, but outside of that, it's a little bit cumbersome in my industry for food and beverage to use 3D printed parts, because we can't really have porosity. So that's something that you have to consider. That comes up a lot in castings, 3D printing, sometimes in injection molding, depending on how thick the part it may be. The other factors are cost and time. I can't tell you how many times we've had to throw out ideas simply because the lead time on the part was about 20-30 weeks, and that idea just does not work for our customers. And sometimes cost is a huge factor, where we actually just recently got, so I mentioned that part, let's see, this impeller here, this actually was going to run, just to do one sample of a 3D printed of this, was going to run us anywhere between $3,000 to $4,000. So that also doesn't exactly work when you're trying to sell the whole pump for that same price. So I wanted to show you guys this video that incorporates another pump that we sell, and to kind of go back into the interactions as well of each of the parts. So these screws are originally cast, and then what we do is we actually turn these on a 5-axis mill slash, well, at that point it becomes a 5-axis turning center. And the reason for that is so that each of the screws are so tightly toleranced to each other that it looks like they're touching, but what they're actually doing is creating small pockets, small voids in between each one of the rotors, such that the fluid and those balls can actually sit into and travel through the pump up and over without any damage. So that is something that we actually had to really consider a lot of manufacturing time on, because the incorporation of a 5-axis machine, along with starting off with a casted part, doesn't sound like it would be a whole lot, but it's a little bit more than you'd imagine. Several months actually kind of went into just one rotor development for that. And so finally, step 5 really comes down to the CADs. Let's see. Yeah. And so step 5 is finishing off with modeling and drafting. Honestly, you know, I know that the talk today was supposed to be more about the CAD development side of things. But really, once you get all steps 1 through 4 accomplished, step 5 is really essentially done for you because you have a general shape. You're aware of the different manufacturing processes. You know what their limitations, capabilities are, and you know what your reactions or you know what your loading is going to be like for that part. So the modeling portion really just comes down to, are you clear and concise with your dimensions? Does the manufacturer understand what's going on, as well as the people that are assembling the components? Do they understand what's going on? So a standard that's commonly used is the ASME 14.5, but that's not necessarily you know, all that you have to stick to. Really what I like to think of for modeling and drafting is it just comes down to fun. Just enjoy yourself and really, you know, let the skies be the limit. Let your imagination run wild. So if, so yeah, beyond that, are there any questions?
So if you do have any questions, you can just put them in the Q&A at the bottom of your screen. Yeah, so we'll just give everyone 1 second to type in a question if they have one. Okay, so we have one question. So what is one of your favorite things or coolest things that you have CAD'd or designed?
That's tricky. Honestly, it would have to be a sensor. At my previous company, I developed a sensor pickup housing that allowed the sensor to swivel 360 degrees without any sort of binding. That took me a long time, but I tell you, it was so much fun to actually work with our manufacturers, because that also involved a lot of cast materials. We had to work with our machine shop on some very, very weird fixturing that I won't get into too much details, but let's just say that the fixtures for that were about 10 times more than the actual project plan for the parts. So it was a hot seller, so we did end up making the money back. But yeah, that would have to be hands down one of my favorite projects I've worked on.
Awesome. Thank you so much. We hope all the teams learned a lot about different options on how to design some parts.